Hello, hello. This is Unit 11 Gases. This is the very last chapter of this entire year before we can enjoy a beautiful summer. So we're going to get started with bases. Now, it's a multitude. It's a solution of things, but the three most abundant, I want you to know, are nitrogen, about almost 80%, oxygen, a little over than 20%, and argon's about 1%. The rest of these, they vary based on temperature, altitude, and just general region of space. So know that that's what you're breathing. So when we talk about gases, generally there's only a handful of things that are going to be found in the gaseous state. So in terms of elements, you can see the ones listed in blue are naturally found as gases. And then here's a nice list of substances. Now, at normal temperatures of room temperature and pressure, again, that's what you're going to find is they're generally smaller molecules, because as soon as you start getting up into 10 or more atoms, they're going to have different intermolecular forces that would want to pull them together and condense to a liquid. So larger molecules have higher boiling points. So again, most of these are going to be fairly small. And this is at normal temperature. So you could vaporize larger things to a gas, but it would take higher temperatures or really, really low pressures. So some of the things we're going to look at first is stuff you already know. So the physical characteristics of a gas. So we know that gases, we know they're fluid. Again, we normally reserve that word fluidity, or we tend to use it for liquids, but fluidity is a property of liquid in that both of them down here, liquids and gases, don't have a set shape. They change their shape to their container. That's what it means to be fluid. They flow. Um, and so liquids and gases are both fluid. Now, what makes them distinct is that gases can also change their volume. They are compressible or they can expand, where liquids, while they're fluid, that doesn't happen. Now, gases will always mix nice and evenly and completely, so they form homogeneous mixtures. Now, this is sometimes true for liquids, but we talked about like dissolves like. So similar polar liquids will mix, but we know oil and water, polar, non-polar, they do not. But that's not true for gases. In the gas state, they all mix completely regardless of polarity. So polarity is not even, we won't even talk about polarity in this chapter besides to say like, hey, it doesn't really matter. So that's nice. The volumes and pressures the volume and pressure is very sensitive to temperature. Now, you could technically heat up a solid and a liquid and change its volume, but it's a pretty insignificant amount. But gases, they can drastically change in volume and pressure with temperature. They have significantly lower density. So solids and liquids are called the condensed phases, meaning, when things are dense with density, they're clustered together, but gases are very spread out. So while these are the condensed phases, gas is the non-condensed phase. Again, just for comparison, if you were to take liquid nitrogen, it has a density as a liquid of 0.807 grams per milliliter, or 807 grams in a liter. So this is liquid nitrogen below 77 Kelvin, so really cold. But if you were to allow it to vaporize, it would expand and take up 650 times as much space. So the density is much lower. Normally when you talk density, you normally report in grams per milliliter, but for gases, it'll be in grams per liter, just of how small. This is a fantastic link. You should click on and watch. If you do, you'll be treated to the pleasure of this goofy guy inhaling sulfur hexafluoride, and it's just a delight. We watched it your sophomore year, and I won't hit play on it again, but you definitely should. So some terms that we'll use: diffusion and effusion. Diffusion, like here you're seeing this partition removed and the gas particles spread out uniformly. That's diffusion, and you can measure it in terms of velocity, meters per second. So how fast are particles traveling? Effusion, on the other hand, is looking at how quickly do particles move through a hole or a pore, and this is measured in terms of time. Now, the reason we have both terms is while diffusion is more common, it's easier to measure or visualize effusion. Like if I were to try to track how long would it take for the air I breathe out to travel across the room, to diffuse across the room, you can't really see it to measure it. But if you have a gas tank or a balloon that you're slowly letting the gas seep out, it's a lot easier to see the pressure or volume drop, and then you can measure the effusion time. And since they're governed by the same kinetics, the same physics, you can, by knowing one, you can figure out the other. Again, when we use the word fluid, it doesn't just pertain to liquids. Gases are also fluid. Every time you walk through a room, wave your arms, gas particles are fluidly moving around them, allowing you to do all those fun motions. But because gases are so spread out, the light doesn't interact with them very much, and they're invisible to us. Again, here's a picture of dry ice. You know what it looks like when, as it sublimates. So at that point, as soon as it sublimates, it's dense enough that you can see its kind of fluid properties. Now it's helpful to measure gases in terms of pressure. Again, if you have a gas tank, typically it'll have a manometer, something that measures the pressure, to tell you how much gas is in there. And so we'll come back to this several times. But I want you to know that pressure is a measurement of how much force divided by a certain area. So the force in this chapter will be gas particles that are moving around and colliding with the surface. But then depending on how much it's actually colliding with will determine pressure. So pressure is what you actually feel. Again, this garden hose, there's a force of water coming out that's determined by the velocity of it moving. But whether you push the nozzle or not changes the area. And so you can make the same hose kind of lightly, have water come out slowly, or like a jet where the force isn't changing, but as you decrease the area, the pressure goes up. And here we have stepping on a bed of nails, and you probably know not to step on one nail, but if you increase the number of nails, you increase the area, and that decreases the pressure. So your force doesn't change. The force here would be your body weight, your mass times gravity, but what you feel is the pressure. So the more area you have, the lower the pressure. I have the bow staff and the sword down here. Again, if you got struck with one of them, you could probably imagine that with one, you're going to have like a broken arm, and the other, you're going to have like one arm removed. Now, when you get hit with them, the same force is being applied. But anytime we talk about something sharp, like a blade, what's significant is that it's putting all of the force in a really, really, really tiny area, which greatly enhances the pressure and removes your arm or whatever appendage. Historically, the way we measure air pressure is through a barometer. Today we have digital ones that do it a little bit different, but the earliest forms used water, but they eventually found it was way more efficient to use mercury. So here is a glass tube filled with mercury that is inverted in a pool of mercury, and it is open to the surrounding atmosphere. So imagine air particles colliding with this surface. Collide, collision, 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 collision. And the stronger the collision, the greater the force, or the lower the area, the greater the pressure, and it pushes this level of mercury up the tube. So what they found hundreds of years ago is in this setup, in a 1 centimeter diameter tube, that at sea level, it could push it up 76 centimeters. And this is going to give us this weird unit of pressure called millimeters of mercury. So 76 centimeters is 760 millimeters. And we're going to say at sea level that air pressure is 760 millimeters of mercury. And so there's a lot of different types of units. The SI base unit is the Pascal, where it's derived from newtons per meter squared. A Pascal is about 100. It's like 1 in 100,000th of an atmosphere. Oh, down here, 101,000 pascals in an atmosphere. Now, again, the ones that we're going to use are more common with the barometer. So 1 atmosphere, which is what you're feeling right now, is 760 millimeters of mercury, where that's also sometimes known as a torr. Now, in the US, probably the most common unit of pressure we're familiar with is PSI, that is pounds per square inch. Again, pounds is the unit of force, inch squared is the area. 14.7 pounds per square inch. If you've ever filled up your car tires, it's probably somewhere around 40 psi. So there's a couple different factors for atmospheric pressure. Again, the biggest one is elevation. So you can literally think of air pressure is, again, if you think of swimming, when you go underwater, if you've ever dove down in the deep end, you felt water pressure, where it's literally just sitting on top of you, and that force over your body is just added pressure. But then air pressure, you can think of it as this column of air miles and miles and miles above that sits on top of you. So at sea level, you have 1 atmosphere, but if you go up 4 miles, it's cut in half. If you go up another 6 miles, you're down to a fifth. And so the higher and higher up you go, there's less particles pushing down on you. And again, it's just the force of gravity pulling them all down on top of you. And so as you go up in altitude, so does atmospheric pressure goes down. And then temperature and weather definitely affect them as well, but we're not going to worry too much about them. This is where I would normally like to talk about straws and suction cups and those types of things, because I do want you to know that suction is not a pulling force. It's not a sticking force. You know, if you put a suction cup on something and it's sticking there, it's not because it's pulling to the wall. It's because it lowers the pressure on the other side, and then atmospheric pressure is able to just hold it there. Suction cups and straws, you can watch this video about straws because that sounds fun. They both work under the same concept of lowering the air pressure on one side, and then the higher air pressure will push it up. So suction is a pushing force, not pulling. Again, when you're thinking about this pressure, think on the molecular scale that there's just billions and billions of collisions that are happening over and over and over. And so as the number of collisions go up, or the force of collisions goes up, that increases the pressure. But also as the area gets smaller, that would also increase the pressure. Here's a fun video about air. Now, there's a little math in this chapter. Here's a super simple one. If you go up to the top of Pikes Peak, your barometer might read that it's 468 millimeters of mercury. Well, what is that in atmospheres? So you only need to know that 1 atmosphere is 760 millimeters of mercury. So going back a couple chapters, we just need to know how to do dimensional analysis. We divide by that same unit, and we have 0.62. So only about 62% of your normal air pressure you would have at sea level. Now, we talked about physical characteristics of gases, and you pretty much already knew those. But now what we want to do is connect them to the kinetic molecular theory. So again, we can visually see the properties of gases, but theories help us explain why they act the way that they do. So these are molecular theories and kinetic molecular, so the movement of molecules, that help us understand why they act the way that they do. And so for each one of these, I want you to be able to cite an example, know the implication. So the first one, gas is made up of molecules that are separated but from each other by very large distances compared to their own dimensions. And so what we mean by that is if here's a sample of gas, that when you zoom in, each particle is considerably farther from other particles in comparison to their own volume. So we can treat each gas particle like it has insignificant volume. And so it doesn't matter if it's tiny helium or larger argon or larger xenon. So because these particles are going to be so spread out anyway, none of that matters what their actual radius is. So this accounts for their very low densities because there's so much of a gas that is just empty space. This is also why gases are so compressible. Since there is room for them to get closer together, they are able to be compressed. Again, solids and liquids are already too close for that to happen. And just for some numbers, if you were to take normal room temperature air at normal pressures, if you could condense all of the gas down, it would only make up 0.2% in terms of the actual volume of oxygen and nitrogen. And then the other 99.8%, that's just empty space. Number two, particles in a gas are constantly in motion and they're traveling in random directions. So again, this is part of that whole fluidity concept. And these particles are said to frequently collide, and they collide elastically, meaning they impart energy or absorb energy from the particles that they collide with, but none of the energy is in terms lost. So again, any one of these particles is always going to be moving. Now, any given collision might make them speed up or slow down, but the energy involved is conserved. And so later, when we talk about the speed of a gas, there won't be one speed, it'll be a distribution. And so we'll always talk about the average speed of a gas particle, not, oh yeah, every particle is traveling exactly 300 million or 300 meters per second. Now, this is also why if you measure the gas speed, like how fast a particle is moving, it will be different from the diffusion speed, because if you pop a balloon or spray some perfume and you're waiting for the gas to travel across the room, it's not traveling in a straight line. It's bouncing around forward, backward, and eventually it's taking the detoured route. And so diffusion rates will always be much, much slower than the actual velocity of a gas particle. It's calculated that they travel about 500 times their own size between each collision. So about every 70 nanometers, they're colliding and changing directions. So this is how we explain why gases diffuse and effuse. So since they're always moving, if you change the container, they just keep on moving. So they change to the shape of the container because they're always just going to be colliding. There's no set pattern or direction. It's just completely random. Number three. So this is going to touch back on a chapter we covered your sophomore year that is covered more in depthly in College Chem 2. But gases exert neither attractive nor repulsive forces. These are normally called intermolecular forces. So again, if here's a gas and we say that all the particles are really spread out, the forces, because they're so spread out, they're too far apart to actually attract or repel each other. So we say the intermolecular forces are negligible. That is, they're not zero, but they're so small that they really don't matter. And if we look at liquids and solids, if we talk about the hydrogen bonding in liquid water, they have to be within like 5 angstroms, which is angstrom is 10 to the negative 10. You don't have to know that, but they have to be in close proximity to be able to have these types of interactions. But in the gas state, they're so spread out that it doesn't matter. Again, intermolecular is between molecules. So again, this one explains why gases mix homogeneously. They're too far apart to care whether the next molecule is polar or nonpolar. So they're just going to keep on moving randomly, and so their own identities don't dictate how they mix. The last part is that the average kinetic energy of a molecule is proportional to temperature. So from physics, you should remember that the kinetic energy of something is 1/2 times its mass times velocity squared. Again, this line over here is just noting that it's average velocity. Well, using this, we can point out that as temperature goes up, as far as kinetic energy goes up, mass isn't going to change. It's velocity that's going to change. And so with greater temperature, we get greater velocity. So faster gases have particles that move faster. So this part helps indicate why that as temperature goes up, it's going to affect things like pressure and volume, because with more pressure, higher temperature, as they move faster, that's going to lead to more collisions. Another component of this is that if you have two gases at the same exact temperature, they will have the same average kinetic energy, regardless of their size. So keeping that in mind, let's say we have two comparable gases, helium and chlorine, and let's say they have an arbitrary kinetic energy of 5. So at the same temperature, they have the same kinetic energy. So the only thing different, again, we don't care about polarity. We don't care whether it's one or two atoms. The only things that matter are the temperature and the mass. And so if you put in their masses and calculate for velocity, you get these numbers. Now, these numbers don't really mean anything because I just made up this number 5 just to make the math easy. But if we take a ratio, we get this. And so what it's telling us is that at this temperature, helium is moving 4 times as fast as chlorine. And so that's what we should expect. So as the mass goes down, velocity goes up. Again, if I asked you to throw a bowling ball and we clocked the speed compared to a baseball, you would expect, throwing with the same force, you would expect with lower mass, you could throw the baseball a lot faster. And the bowling ball with greater mass, lower velocity. So those two things are inversely proportional.